Hello everyone, myself Guru Joshi. Today we are going to study a topic named curve tracing. So let's start with the first topic, that is a tracing of Cartesian curve. Curve sketching is the procedure to obtain an approximate shape of the curve without plotting a large number of points on it. Okay. Now the graph of a given function is helpful in giving a visual representation of the behavior of a curve involving the study of its symmetries, asymptotes, the interval in which the curve is increasing, decreasing, and its concavity, etc. Okay, so let's discuss the method. The points to be taken into consideration while tracing a Cartesian curve. So the first one is symmetry. Now the curve is symmetric about x-axis. When we can say that the curve is symmetric about x-axis if the powers of y occurring in the equation are all even. Okay, just observe the equation. Okay, and if the powers of y are even, then we can say that the curve is symmetric about x-axis. The curve is symmetric about the y-axis if the powers of x occurring in the equations are all even. Okay, so if the powers of x are even, then it is symmetric about y-axis. Also, we can use this to check whether the curve is symmetric about x-axis or a y-axis. So for x-axis, we have f of x minus y will be f of x comma y. Okay, and for y-axis we have f of minus xy is equal to f of xy. Okay, next one, the curve is symmetric about the line y is equal to x if on interchanging x and y the equation remain unchanged. Okay, so in the given question just interchange x and y, and if the question remains same, then we can say that curve is symmetric about the line y is equal to x. Now, the curve is symmetric about the line y is equal to minus x if on replacing x by minus y and y by minus x, okay, the equation remain unchanged. Again, if you will substitute x by minus y and y by minus x, and if the equation remains same, then we can say that the curve is symmetric about the line y is equal to minus x. Now the curve is symmetric in opposite quadrant or about the origin if on replacing x by minus x and y by minus y, the equation remain unchanged. Okay, so if you will substitute this, then we can say that the curve is symmetric in opposite quadrant or about the origin. Okay, now the next one is origin. So the curve passes through the origin if there is no constant term in the equation. Okay, again we have to check from the question that if there is a constant term present or not. Okay, if no constant term is present, then we can say that this curve passes through the origin. Now, if the curve passes through the origin, the tangent at the origin are obtained by equating lowest degree term in x and y to 0. Okay, so if we have a curve and it passes through the origin, then we have to find the tangent at origin. Okay, and that we can find by equating lowest degree term in x and y to 0. Okay, now if there are two or more tangents at the origin, then it is called a multiple point. Okay, if we are having two or more tangents, then origin is called a multiple point. Now there are three types of multiple point. Okay, they are node, cusp, and isolated point. Now the point is called node if the tangent at these points are real and distinct. Okay, so if the tangents are real and distinct, we can say that it is a node. If the tangents are real and coincident, okay, then we can say that it is a cusp. And if the tangent at that points are imaginary, then the point is called a isolated point. Okay, so we have to remember this trick. Now, point of intersection. The point of intersection of the curve with x and y axis are obtained by putting y is equal to 0 and x is equal to 0 respectively in the equation of a curve. Okay, so if we want to find the intersection with the x axis, we have to substitute y equal to 0, and to to find the intersection with y-axis, we have to substitute x is equal to 0. Okay. Now the tangent at the point of intersection is obtained by shifting the origin to this point and then equating the lowest degree term to 0. Okay. And after finding the point of intersection, we have to find the tangent at that point of intersection. Okay. So what we'll do, we'll shift the origin to that particular point. Okay. And then to find the tangent, always we have to equate the lowest degree term to 0. Now we'll define the region of existence. So this region is obtained by expressing one variable in terms of the other. Okay, so we will write like this: y is equal to fx, or we can write x is equal to fy according to the question, right? And then finding the values of x at which y becomes imaginary. Okay, so if we are writing y is equal to fx, okay, so what we need to do is we have to find the values of x, okay, at which this y becomes imaginary, right? Now the curve does not exist in this region which lies between these values of x. Okay, so for that values of x, when y is becoming imaginary, okay, so curve will not exist in that region. So in this way we can find the region of exist. Now the next is asymptotes. Asymptotes parallel to x-axis are obtained by equating the coefficient of highest degree term of x in the equation to 0. Okay, now if we want to find the asymptotes, okay, parallel to x-axis, then we have to equate the coefficient of highest degree term of x to 0. Okay, and to find the asymptotes parallel to y-axis, okay, we have to equate the coefficient of highest degree term of y in the equation to 0. Okay, now oblique asymptotes are obtained by the following method. Now to obtain oblique asymptote, what we need to do, substitute y is equal to mx plus c in the given equation. Okay, then simplify the equation, okay, and equate the coefficient of highest power of x and next highest power of x to 0. Okay, and by this solving this equation, okay, we have to find the value of m and c respectively. And after finding the value of m and c, substitute over here, okay, so you will get oblique asymptote. Now let's see the interval of increasing and decreasing function. Now the curve increases strictly in the interval in which dy by dx is greater than 0. The curve decreases strictly in the interval in which dy by dx is less than 0. Okay, and the curve attains its maximum and the minimum value at the point where dy by dx is equal to 0. Okay, now let's solve one example, okay, to understand this better. So trace the curve y square into 2a minus x is equal to x cube. Okay, means we need to draw this curve without plotting the points, okay, using these properties. Now the first one is symmetry. Now as you can see in this, okay, here we have y square, here x and x cube. So the power of y is even. Okay, therefore we can say that the curve is symmetric about x-axis because the power of y is even. Now origin. Now we'll check whether the curve pass through origin or not. So if you will multiply y square inside, okay, so you will get 2ay square minus xy square is equal to x cube. So we do not have any constant, okay. So the curve passes through the origin as there is no constant term in the equation. Okay. Now the curve is passing through the origin, so we have to find the tangent at origin. Okay. So we'll equate the lowest degree term to 0. Now this is y square, okay. Now x into y square, so total degree will be 3, okay, and here x cube, so its degree is 3. So the lowest is what? 2ay square, okay. So uh, so 2ay square is equal to 0. So from this we will get y is equal to 0, okay. Therefore y is equal to 0 means x-axis. So we can say that x-axis is the tangent at the origin, okay. Now we'll find the point of intersection. So for that, substitute y is equal to 0. So if you will substitute y equal to 0, this whole term is 0. Okay, so answer of x is 0. Okay, therefore we can say that point of intersection is origin. Now we'll find the region of existence. Okay, so from the equation we are making y as a subject. Okay, so y will be what? Plus or minus under root x cube upon 2a minus x. Now this x cube we can write as x square into x. Okay, and that x we can bring outside, so this is plus or minus x under root x upon 2a minus x. Now we have to find for which value of x this y becomes imaginary. Okay, so this y becomes imaginary when x is less than 0. So first consider this. Okay, if this x is less than 0, okay, so negative will come with this under root. Okay, so it will become imaginary, right? Or when this 2a minus x is less than 0. Okay, so if 2a minus x is also less than 0, then this y becomes imaginary. So from this we can get that x is greater than 2a. Okay, so we have two conditions, that is x less than 0, okay, and x greater than 2a. So we can say that in the region minus infinite to 0 and from 2a to infinite, okay, in this two region the curve does not exist. Why? Because in this interval y becomes imaginary. Okay, so where does the curve lies? Right, so the curve lies in the between region, that is 0 to 2a. Okay, so we will keep all this thing in mind in order to trace the curve, right? So just keep in mind that the curve lies in 0 to 2a. Now asymptotes. Now to find the asymptote parallel to x-axis, what we have to do, we have to equate the coefficient of highest degree of x to 0. Okay, now from here highest degree of x is 3 over here. Okay, its coefficient is 1, that is constant, right? So we can say that since the coefficient of highest degree term of x is constant, there is no asymptote parallel to x-axis. Now to find the asymptote parallel to y-axis, what we have to do, we have to equate the coefficient of highest degree term of y to 0. Okay, now the highest degree of y is 2a minus x. So we'll equate 2a minus x to 0. So from this we will get x is equal to 2a, which is the asymptote parallel to y-axis. Okay, now we'll discuss the interval of increasing and decreasing function. Okay, so y square into 2a minus x is equal to x cube. So from this we'll get y square is equal to what? X cube upon 2a minus x. Now differentiate this with respect to x. So you will get 2y divided by dx is equal to, now to solve this we have to apply division rule. Okay, so this denominator as it is, derivative of numerator is 3x square minus this numerator as it is, and derivative of denominator is minus 1 upon denominator square. Simplify this. Okay, bring this 2y over here, so dy by dx is what? 1 upon 2y. X square take out common, so x square into 6a minus 2x upon 2a minus x whole square. Okay, now since this curve is symmetric about x-axis, okay, we'll consider the part above x-axis, that is y greater than 0. Okay, so this y we are considering it greater than 0 because the curve is symmetric about x-axis. This is whole square, so it is always greater than 0. Okay, so this again x square is also square, so this is greater than 0. Okay, so what we need to see is 6a minus 2x is greater than 0, then this dy by dx is greater than 0. Okay, that is when x is less than 3a. Okay, so we can say that the curve is strictly increasing in which region? 0 to 2a. Now here we have x less than 3a, but here we are writing 2a because the region of existence is what? 0 to 2a. Okay, so this curve is strictly increasing in this region. Now as we have discussed that the curve is symmetric about x-axis, so you can see that it is symmetric about x-axis. Okay, now it meets at origin. Okay, point of intersection is origin, and asymptote is what? X is equal to 2. Okay, so this curve will go infinitely in this parallel to this asymptote, right? So this is how we trace this curve. All right, so I hope you have understood throughout the session. Thank you for watching.